Hello everyone. In this video, we are going to learn about measurable functions and random variables. So in this video, we are going to define what a random variable is, and we will also go through the basic properties of random variable, and we'll discover what is a cumulative distribution function. So let's start with first defining a measurable function. So if you have seen the previous video about measure space, you would know that a measure space would look like this, where let's say for an arbitrary sample space omega, there is a sigma algebra f which is defined on omega. So f is a sigma algebra on omega, and there is a measure mu such that it would follow this property, that the measure of null set would point to 0 and the measure of countable union of disjoint sets AI, where all AIs are disjoint, this would be nothing but summation of measure of all of these individual AIs. And all of the AIs, let's say A1, A2, all of them are disjoint. That means the intersection of any two of them would be the null set. Okay, now this is a measure space. And what is a measurable space? In measurable space, we don't need to define the measure mu. We can just work with the sample space omega and its sigma algebra f. Okay, so we only need these two entities for defining a measurable space. Or you can say that a measurable space is such a space on which you can define a measure. So we only need omega and f. So this is a measurable space if f is a sigma algebra on omega, which is our sample space. And for f to be a sigma algebra, we had known the previous conditions that it should be a non-empty set, it should be closed under complement, and should be closed under countable union. So now we know that omega and f are measurable spaces. Similarly, let's say there are two measurable spaces. Okay, we are defining two measurable spaces, omega 1 f1 and omega 2 f2, where f1 is a sigma algebra on omega 1 and f2 is a sigma algebra on omega 2. Okay, we can actually denote it like this. So let's say we have omega 1 here, we have some sets present in our f1. So let's say this set is present in f1, it is an element of f1, a1, a2, something like that. Similarly, we can define a sample space omega 2, and inside this we can define the subsets, and this can be f2. Okay, so now we have two measurable spaces. Now we define a measurable function f such that its domain is omega 1 sample space and its range is omega 2 sample space. Okay, so it points from omega 1 to omega 2. So this is the domain of f and this is the range of f. Now what does it say how do we determine if f is a measurable function? So For every A2, so A2 is an element in the F2 sigma algebra, the pre-image under F, which is F inverse of A2, which would be some event in the sample space omega 1. So this F1 inverse of A2 should be present in the sigma algebra F1. Okay, so that was quite a mouthful. Let's simplify it. Okay, so let's say we have, I'll remove this. Okay, so this is our sample space omega 1 and this is our sample space omega 2, this denoted by these two circles. Okay, let's say there are some disjoint sets here. For simplicity, I'm taking a disjoint set. It could be a non-disjoint set as well. So let's say there is a set A21 present inside the sigma algebra of omega 2. So let's say A21 belonging to F2, where F2 is a sigma algebra on omega 2. Okay, so A21 is present in F2. Now let's say a function a measurable function f maps from omega 1 to omega 2. Okay, so let's say it has some set here, let's say a11. So f of a11, let's say it maps to a21 in omega 2 sample space. Okay, so this maps to this. So taking a pre-image of any set, what does taking a pre-image means? So taking a pre-image means an inverse function. So f of a11 is a21. So if I take a pre-image of the set a21, it would point towards a11. So you can also write it in this way: f inverse of a21 is equal to a11. So this is called a pre-image. Okay, now for f to be a measurable function, every set A2 which is present in the sigma algebra F2, if we take a pre-image of every such set, it should point to a set here present in the sample space omega 1, and that set should be present in the sigma algebra of omega 1, which is F1. Okay, so let's see how. So let's say I take any set present in the sigma algebra sigma 2. Okay, let's say a1 a23. So a23 is present in F2, where F2 is a sigma algebra on omega 2, and we take its pre-image back to omega 1. Let's say there is a some set which satisfies this condition. So let's say f inverse of a23 is equal to, let's name it a13. So this set here highlighted here is a13. Now this set a13 should belong to F1, where F1 is a sigma algebra on the sample space omega 1. Okay, so I hope this makes it clear. So let's proceed with this measurable function definition.